Let's take a look at what happens in a simplified setting, namely a setting in which there are only two candidates. Now, when there are only two candidates, let's call them A and B, then it seems that all of the voting methods that we've been considering all give the exact same result. That is, all of the voting methods reduce to the simple majority rule. The majority rule when there are two candidates just simply says A is ranked above B, just in case there are more voters that rank A above B than B above A. It says that B is ranked above A if there are more voters that rank B above A than A above B. Otherwise, A and B are tied. Now, the question we want to ask now is, when there are only two options, can we argue that majority rule is the best procedure? And the approach or the perspective we're going to take in this lecture is an axiomatic one. We're going to argue that majority rule is the only group decision-making method, when there are only two candidates, that satisfies a certain set of very natural and desirable group decision-making principles. So let's be a bit more formal. Let N be a set of voters. So N is going to be our set of voters, and X is our set of candidates. So we have just two candidates, A and B. Now, a social welfare function is going to be a function from the set of profiles, so those are sequences of orderings over X, to orderings over X. So it's a function that associates with every profile an ordering over X. Now, O of X denotes the set of orderings over X. Since X contains only two candidates, there are only three possibilities, namely the ordering in which A is ranked above B, the ordering in which B is ranked above A, and finally the ordering in which A and B are tied. So A and B are ranked at the exact same level. Now, majority rule is the function that associates or assigns to a profile R the ranking A is ranked above B, just in case there are more people that rank A above B than B above A. It assigns the ranking A and B are tied, or there's an indifference between A and B, when the number of people that rank A above B is equal to the number of people that rank B above A. And finally, B is ranked above A if the number of people that rank B above A is greater than the number of people that rank A above B. Now, in this setting, we can simplify the notation a little bit. This will just help us not be so notation heavy. The way we're going to do that is, instead of writing APB for the ordering in which A is ranked above B, I'm going to write the number 1. We're going to write 0 for the ranking in which A and B are indifferent, and -1 for the ranking in which B is ranked above A. In this case, a social welfare function is going to be a function that maps sequences of 1, 0s, and -1s to either 1, 0, or -1. And now we can rewrite what the majority function is, since when V is a sequence of 1, 0s, and -1s, I'll use this boldface V rather than the boldface R. So this is the majority function in this updated notation. Now, of course, this NR of either 1, 0, or -1 is just the number of voters, or the number of position in which there's a 1, 0, or -1 in that position. Now, what are the principles that we want to impose? We're going to start with three very natural and desirable properties: unanimity, anonymity, and neutrality. Unanimity says if there's unanimous support for some alternative, for some ranking, I should say, then that must also be the social outcome. So formally what this says is if for any vector, if you give me a vector of 1, 0s, and -1s, and that vector happens to be uniform, so it happens to be either all 1s, all 0s, or all -1s, then the outcome has to be either 1, 0, or -1. So what this says is that f of 1, when we have a vector of all 1s, that outcome has to be 1. F of a vector of all 0s the outcome has to be 0, and f of the vector of all minus 1s has to be minus 1. So we start by just simply explicitly saying when everybody agrees, then that's what the outcome has to be. The next assumption is anonymity. This just says all voters need to be treated equally. This just says that if you have a sequence of 1s, 0s, and minus 1s, and you shuffle them around, then that shouldn't change the outcome. So for example, f of 1, 0, minus 1 has to be equal to f of 0, 1, minus 1, which has to be equal to, say, f of 1 minus 1, 0. Because all of these are simply shuffling arounds of the 1, 0s, and minus 1. So the outcome depends only on the number of 1s you see and the number of minus 1s, not on where they show up in the particular sequence. And finally, there's neutrality. And neutrality says if we swap A and B in everybody's ranking, then the outcome has to swap accordingly. So what it means is that if, for example, f of 1, 0, 1 was equal to 1, then if we swap A and B in everybody's rankings, what that means is that people who had A ranked above B now have B ranked above A. And similarly, and if A and B are tied, then of course if you swap A and B just remain tied. The outcome has to change accordingly. So the outcome in this new setting needs to be minus 1. So f of minus v, so minus a vector of numbers, is just minus each one of the elements, each one of the components of that vector. And finally, the key axiom is what May called positive responsiveness. Positive responsiveness is just an idea of monotonicity, that if more people support you, then that should help you in the election. What positive responsiveness says is that if we're in a setting in which we have a sequence of 0s and 1s, so we have a set of votes, we're in some election scenario, and people have voted, and A and B are tied, or A has come out on top, A is ranked on top. Now, if we move to a new election scenario, so we're in a different election scenario, but this is a special election scenario where candidate A has gotten some more support. And what that means, there are two ways to understand that. It means two things. One, either there were some people that ranked B above A and decided to swap and rank A above B, so you change a minus 1 into a 1, or there were some people that treated A and B as tied and decided that A should be ranked above B. Or, and this is an important third case, there are some people that ranked B above A, but they decided that candidate A and B should be tied. So they move from minus 1 to 0. If any of those three cases happen, if the shift from the one election scenario to the other involves a move in favor of A, then the outcome has to be candidate A wins. The intuition is that if more people throw their support to you, where support is understood in a weak sense, in the sense that if you say that A and B are tied, or you're indifferent between A and B, then you're throwing your support to both A and to B. In that case, this is the monotonicity axiom. What May proved in 1952 is that a social decision method F satisfies unanimity, neutrality, anonymity, and positive responsiveness if and only if it's the majority rule. So if you look at the space of all possible group decision-making methods, what that means in this case is the set of all function that maps sequences of 1, 0s, and minus 1 to 1, 0, or minus 1. You look at the space of all of those functions. One of those functions in there is majority rule. It turns out that these four properties uniquely pick out majority rule. So there's two things we have to prove here. First, that majority rule actually satisfies all of these properties. Now that's actually rather straightforward, and I will leave that up to you. It's a really good exercise to make sure you understand the notation and what these principles say if you can go ahead and prove that majority rule satisfies all these properties. I'm not going to give you a formal proof, but I just want to give you the idea of a proof, a sketch of the proof, how we go in the other direction. If I tell you that I have a function, a group decision, a social welfare function that satisfies these 4 properties, I need to be able to prove that it must be the majority rule. So how do we do that? Well, we'll consider 2 cases. The first case, suppose we just have a setting where we just have 3 candidates, 3 voters rather, sorry, 2 candidates of course, but 3 voters. Now, if we're in a setting in which candidate 1 says A is ranked above B, candidate 2 says A and B are tied, and candidate 3 says B is ranked above A, in that setting, of course, we would want to argue that A and B should be tied. So the outcome here should be 0. But let's suppose that instead we have some function that assigns either 1 or -1 to this profile. Now, if that's the case, then by unanimity, we can shuffle these around, and that doesn't change the assignment. So by unanimity implies that -1, 0, and 1 is assigned 1 or -1. Now, this is just simply the shuffling based on the permutation where voter 1 is mapped to voter 3 and voter 3 is mapped to voter 1 and voter 2 just remains fixed. So anonymity implies -1, 0, 1 should be assigned 1 and -1. So again, how does that mean? That means if this profile was assigned 1, then this second profile has to also be assigned 1. If it was assigned -1, then it has to be assigned -1. Now, we're almost there. Neutrality means if we flip all of the bits, if we change the -1 to a 1 and the 1 to a -1, then the outcome has to flip appropriately. So that means that if this profile was originally assigned a 1, then this profile has to be assigned a -1. But this profile is assigned a 1 exactly when the original profile was assigned 1. But notice what we've just proved here, that the profile 1, 0, -1 should be assigned 1 and it should be assigned -1. But that's a contradiction because we assumed that our social welfare method is a function. So it can only assign, it has to pick either 1 or -1 to assign this profile. Similarly with -1, if this profile was assigned -1, then this profile where you permute the voters gets assigned -1. And then if you flip all the negatives to positive and positives to negative, then that same profile has to be assigned a 1. That's a contradiction. The only way not to get yourself into a contradiction is to assign this profile 0. So this is one case. The second special case we have is a case that's similar to this. Suppose that voter 1 and voter 2 rank A above B, but voter 3 ranks B above A. Now, according to majority rule, that should mean that candidate A is ranked above B. But let's suppose that the outcome is assigned either 0 or 1. So instead, you assign the outcome A and B are tied or B is ranked above A. I need to argue again that this will lead us to a contradiction. So let's see. Neutrality is going to imply if I flip all of the bits, so these 1s become -1s, and this -1 becomes a 1, then the outcome should flip appropriately. So the 0, of course, remains a 0, and the -1 gets changed into a 1. So this profile, if this profile is assigned 0 or -1, then this profile has to be assigned 0 or -1. Anonymity, again, means I can shuffle around the voters however I want. So this profile, what I'm going to do, let's say I swap voter 1 with voter 3. So I swap voter 3 becomes voter 1, and voter 1 becomes voter 3. That shouldn't change the outcome. So if this was assigned 0, then the outcome has to be 0. If it was assigned 1, then the outcome has to be assigned 1. Now we use positive responsiveness. Positive responsiveness says if this profile was assigned either 0 or 1, and we move to a new profile in which more people support candidate A, then that new outcome has to be assigned 1. So this profile, let's move in favor of candidate A. So we're going to take voter 2. Voter 2 ranks B above A, and voter 2 is going to change her vote to A and B are tied. Now, according to positive responsiveness, that means that this profile has to be assigned 1. Candidate A has to win, has to come out on top. We can use positive responsiveness again. Now, this second voter decides, well, I'm going to swap, rather than having A and B tied, I'm going to rank candidate A above candidate B. So if you move from 0 to 1, again, by positive responsiveness, this new profile has to be assigned a 1. But this is a contradiction because we started off assuming that the profile 1, 1, minus 1 is assigned either 0 or minus 1. And from that assumption, we've been able to prove that that profile has to be assigned 1. That's impossible since our group decision-making method is assumed to be a function. Now, there are a number of other characterizations of majority rule. We don't have the time to go over all of these different characterizations, but I encourage you to take a look at some of these other articles to get different. It's the same basic idea. Roughly, most of them end up focusing on the positive responsiveness axiom and weakening it or changing it in some way.